All right, so this week we're going to start off finishing section 1.3. If you remember, we ended with 1.3 talking about the vertical line test. Tells you if something is a function or not. I think that was it. It was the very last thing we had talked about. Okay. The first thing we're going to talk about here is what's called the greatest integer function. Okay. It's a very simple function. Has kind of an interesting look when you graph it. But the greatest integer function is just defined to be the greatest integer that's less than or equal to x. So in other words, you give me any number you want, and I will give you the biggest integer that I can that is less than or equal to the number you gave me. Can't be more. It has to be less than or equal to the number you give me. The symbol for it, in the book, you'll see the symbol on the left. It kind of looks like a bracket with an extra line in it. On the calculator, we're going to see the abbreviation int, x. So let's try like an example. Let's try, what's the greatest integer you can think of that's less than or equal to 4.3? 4. That's the biggest integer that's still less than that number. So you'll notice here, you're not going to get fractions for answers because the answer is always an integer. How about, let's do 4.99. Still 4. That's the biggest integer that is less than the one you gave me. So what happens all of a sudden when I go to 5? What's the answer now? 5. Now it's 5. So notice all of a sudden it jumps. When you plug in 4.999 repeating, you get 4. When you plug in 5, it jumps to 5. Is there ever an answer between 4 and 5? No. It jumps. So it kind of looks like this.
Cool.
If you plug in an answer between 0 and 0.99999, you get 0. And then all of a sudden when you get to 1, it jumps up to 1. And any answer between 1 and 1.9999 is 1. And then when you get to 2, it jumps up to 2. Okay. Yeah, you see that kind of thing like if you mail a package. You might pay by the ounce. So if your package weighs 14.2 ounces, you have to pay for shipping up to 15. They round it up. You don't pay that exact amount. So like if you pay for 12 ounces of shipping, you can ship anything from 0 up to 11.9 ounces. Once your package hits like 12.1 ounces, then you got to pay the next level up, which covers everything between 12 and 13. All right? So that's kind of how weight works when you ship a package. Now, the reason I did open and close circles is because when you're at 1, it's an open circle on 0 because it has jumped up to the next level. That's why it's a closed circle. All right? So let's graph it on the calculator.
Great.
So on the calculator, it's actually very simple. If you have anything else under y equals, you can clear it. And go to press a couple buttons. So you go to math, and let me find it before I tell you. Yeah. So go to math, then you're going to go over to number, and it's the 5th option down, int. And you just want to put an x in. So x, again, that's right below mode, and close your parenthesis. Okay, so int x. And if you hit graph, you should get something that looks pretty much like what I had on the board. You're not going to see the detail of open and close circles, though. But that's the same thing.
If you put a y in there, would you just get vertical lines instead?
Number 5.
You can't put in a y. You always have to put in an x.
No, if you press
You always
right.
have to put in x. But yeah, there's no way to draw verticals because it's not a function. The calculator only draws functions.
How do I turn off the
So if you still have dots on the screen, because if you remember we did a scatter plot last week, if you go to y equals, plot 1, plot 2, plot 3, make sure none of them are highlighted. So like if I go up to it and hit enter, now plot 1 is highlighted. If there's stuff in plot 1, it's going to draw it. If I don't want to draw it, just highlight it, hit enter, and it turns it off. Yeah. And I did zoom 6. If you had a different window, your steps might have looked a little different. But if you do zoom 6, they should look just like that. Yes.
And how do you get your window back to like the default?
Zoom 6. So this greatest integer function is also known as a step function because it kind of looks like a series of steps. Okay, so it's also called a step function. So this is the kind of direction, if you see this in the homework, find a complete graph, that's on the calculator. Basically, all you'd have to do is write down your x-min, x-max, y-min, y-max. Okay, so we've got a graph, so what I'll do is I'll just take the graph, put it there so you can see it again. I'll go to Window, and I'll grab these values. So that one was -10. So x-min, x-max, y-min, y-max. Okay. And the other thing they want here is the domain and the range. So the domain is what you can plug in. So let's do domain. What numbers are you allowed to plug into the greatest integer function? Yeah?
Infinity to infinity?
Yep, all of them. No matter what number you name, I can always name a number that's less than or equal to your number that's an integer. Always. You can give me a decimal, a fraction. Gets a little tricky with negatives. So like, if I said to you something like the greatest integer less than or equal to 4.2. Yeah, -5, right? Because you think on a number line, it's going to go to the left. So smaller is to the left. So -5 is the biggest integer that's less than or equal to that. Well, you say, what about -4? No, -4 is bigger. It's got to be less than or equal to that. So -5. Okay. So yeah, the domain is all real numbers. -infinity to infinity. How about the range? Do you hit every number from -infinity to infinity in the range?
No.
No.
All integers.
You hit all integers. You never hit like 1.4 because it's an integer function. So there's no fancy way to write it. You could just say the range is all integers. Okay. All right, let's try another one just to practice domain and range. It's not a step function. This is a cubic polynomial with an exponent of 3. Anyone remember what I told you about that exponent in terms of how many times the graph could turn?
It's one less than exponent.
One less. So it could turn twice. Let's see what happens.
Here we go.
16x minus x cubed. X cubed. Okay, I'm going to do zoom 6. Let's see what we got. Okay, do you think that's a good window?
No.
No. It's turning, but it's off the screen. So if the turn is off the screen, that's important. You need to include that in the window. So what do you think I would have to adjust here out of these four values? Yeah, just the y's. Now I don't know exactly what to adjust them to, but maybe we could try like negative 50 to 50 and see if that's, I mean, it'll be better. I don't know if it's going to be enough. Yeah, actually that's perfect. Negative 50 to 50. So now I would say that's a complete graph. All right? Which will now help you to determine the domain and range. I know this graph is never going to turn again off the screen. It can only turn twice. And I'm seeing both turns right now. So it's just going to go up forever on the left, down forever on the right. So let's start with the domain. Would you ever be taking the square root of a negative here?
No.
Nope. Would you ever be dividing by 0?
No.
No. Then the domain is all real numbers. You can take any number you want in qubit. Doesn't matter if it's a decimal. Doesn't matter. And then you can take any number you want and multiply it by 16. Fractions, negatives, doesn't matter. So domain, all reals. Range. So domain is how far left and right the graph goes. And this graph does go left and right forever. Slowly, but it does. How about up and down?
Also infinite.
Yep, it's infinite. And one thing we're going to learn about this kind of graph, a polynomial, is it's continuous. You never have to pick your pencil up when you're drawing. So it's going to go down forever, it's going to go up forever, and you never lift your pencil while doing it. So you're going to go through every number in between, from negative infinity to positive infinity. So any question why the domain and range are what they are here? Right, let's try this one. So I think this will be the last one in, oh yeah, piecewise projectile, okay. So this one says we have a rectangular pool with dimensions 30 by 50. And we're going to put in a sidewalk around the pool that's uniform width all the way around. So maybe like a 3-foot sidewalk all the way around the pool. Okay, but we don't know what the width is going to be. It's just, we're going to call it X. But we know that the area of the sidewalk is going to be 600 square feet. So the question is, how wide is the sidewalk? So we get a lot of information there written out as kind of bullets. What do you think would be helpful in this problem to do? Yeah.
Find the perimeter.
Okay, so we're definitely going to be dealing with maybe some things with perimeter or area. What else would be helpful to do with all this information to make it easier to kind of work with? Yeah.
You might want to draw a diagram.
Yeah, I think if we draw a diagram, it'll make some of this kind of fit together a little better. So let's draw, we've got a pool, and it says it's rectangular, and we're going to put a sidewalk around it, close enough, of uniform width. So my pool, they tell me, is 30 by 50. So 30 by 50. And what does it say that the width of the sidewalk is going to be? X. That's all the way around. Now, one other thing we know that we haven't used is the area of the sidewalk. Okay, so we're probably going to be doing something with area here. So I'm going to call A sub S area of sidewalk. I'm going to call A sub P area of pool. And I'll call, well, actually we might need one more, I'm not sure. We'll call A sub T the area of the, actually, you know what, we'll call it B. Area of the big rectangle. me see how I could get the area of the sidewalk somehow using those three, setting up an equation with those three things.
Can you do something with like the area of the big rectangle would be the area of the pool plus the area of the sidewalk?
Yep, plus the area of the sidewalk, so I'm gonna do the same thing, I'm just gonna rearrange it a little bit, and I'm gonna say the area of the big rectangle minus the area of the pool gives me the area of the sidewalk. So big rectangle minus pool gives you sidewalk. Now there's your equation. We just have to fill in. Okay. So let's start with the hardest one, the area of the big rectangle. What's the formula for area of a rectangle?
Length times width.
Length times width. So I need to know what the length is of that.
It's 50 plus 2x.
Yep, it's 50 from here to here, and then there's a little part there that's the sidewalk and a little part there that's the sidewalk. So it's 50 plus 2x. Yep, good job. So that's my, or 2x plus 50, doesn't matter. That's my length. What's my width?
30 plus 2x?
30 from here to here, and then a little part of the sidewalk on the top and bottom. So 30 plus 2x. Now the area of the pool, we can figure that out. We can get an actual number. What's the area of the pool?
1,500.
Yep, 1,500. And the area that's equal to the area of the sidewalk, which they did, 600. Okay, so let's FOIL out what's on the left and combine like terms and solve for x. So 50 times 30, well, we just did that, that's 1,500. What's 50 times 2x? Plus 60x is 160x, and 2x times 2x?
4x squared.
So plus 4x squared. So that's a certain kind of equation. That's not normally the order we put it in, but does anyone tell me what kind of equation that is?
Quadratic.
Yep, it's a quadratic. Minus 1,500 equals 600. So now we just have to solve that as a quadratic.
So would that cancel out the 2 1,500s?
Yep, that's gone. Now let's put this in standard form. When you solve a quadratic, it's usually equal to what number?
0.
0. So let's do that. 4x squared plus 160x minus 600. Now, these all have something you could factor out or divide through by if you want to make the numbers smaller. What could you divide everything by?
4.
Yep. You don't have to do that, but it does make the numbers a little smaller. Just double check that I did it right. Okay, now we have all kinds of ways we could solve it. We could try factoring. Numbers are a little big, so two numbers that multiply to give you 150 and subtract to 40. Or I don't really think that's going to factor nice, so what's my other option?
Quadratic formula.
Yep, quadratic formula. Does anyone remember how that starts out?
Negative
B.
B plus or minus the square root.
Square root of 4c.
Yeah, I heard a lot. So what comes after the square root?
A.
Not yet.
B squared.
B squared
Minus 4ac
minus 4ac, yep,
over 2x.
over 2a. So let's see what we get. Negative 40 plus or minus 4 times 1 times 150. 600 minus 1600 minus 600. 1,000. So yeah, you're not going to get a nice answer for that. Okay, so let's round it off and see what we get. So we've got negative 40 plus the square root of 1,000 divided by 2. Let's use this one. So negative 40 plus the square root of 1,000 divide by 2. So technically, one of the answers to this quadratic equation is negative 4.19. Any thoughts about that answer?
Can be possible.
Why?
Because we can't accept negative values.
It's a distance, so we can.
Right, we're looking for a distance, right? We're looking for the width of a sidewalk. So yes, that is a solution to the quadratic, but that solution doesn't work in the word problem. So let's try the other one. Negative 40, was it negative 40? Yeah. Negative 40 plus the square root of 1,000.
That's what you did last time.
Oh, then let's do negative 40 minus, the problem is that's going to be negative 2.
Would we just take the absolute value? Or would that happen?
So let's see, make sure we foiled everything correctly. So we got 1,500 plus 100 plus 60x, that looks good, plus 4x squared, okay, equals 600. 4x squared plus 160 minus the 600, that looks good so far. Let me double check that.
I think that 40 is supposed to be positive because you have plus 40x and then you have negative 40 when you put it into the quadratic formula.
Yeah, that's right. Negative b. Yeah, so that part's okay. Negative
Where
b.
does 1,600 come from?
That's b squared, 40 times 40. Minus 4a. C.
Oh.
C was negative 150. So let's do this again. What's negative 4 times 1? So that's negative 4 times negative 150
600.
plus 600. So that's not going to end up being a minus 600. It's going to be a plus 600. What's 1,600 plus 600? 2,200. Now let me double check. But I think that was the problem. Yeah, so it says we should get, they don't actually show all the work because they assume at this point you know how to do quadratic formula, but they said it should come out to about 3.5. So let's see.
Sure.
Is that what it comes out to?
Yeah, 3.5.
Okay, so don't worry about the minus. We already know that's going to be negative. Let's do the plus. Square root of 2,200. 2,200. And if you take half of that, yep, it's going to be about 3.5. So can someone tell me what you got exactly?
3.4520, and there's more than
Okay, 3.452. Yep. So, yeah, just make sure when we do quadratic formula, you don't make the mistake I did. Okay. But it can happen. But at least this time we were doing a real world problem and we saw both answers were going to come out negative. So that was a huge hint something's wrong. Okay, that might not always happen. Okay, any questions on that? Okay, so that's the width of the sidewalk. All right, so one type of problem that's going to come up a little bit in chapters 1 and 2 is projectile motion. So that's basically the motion, like if you were to launch something, kind of like that. It's not a completely accurate formula because really we're looking at projectile motion as a parabola, but it's not really. Projectile motion is more elliptical. If you assume projectile motion is a parabola, you assume gravity pulls straight down. It really doesn't. Gravity pulls in a little bit towards the center of the Earth. So it's almost imperceptible. Like if I were to drop this, it would look like it's going straight down. But it's really being pulled a little bit towards the center of the Earth. So if this is like Earth here, gravity really pulls like this.
So it's only noticeable if you're like really far out?
Yeah, it would really only be noticeable for something like if you were to launch an object from here, like across an ocean. Then you would have to account for the fact gravity is pulling towards the center of the Earth and not just straight down. That's a huge distance, but in a room or even on a city scale, it probably wouldn't have that much of an effect. But halfway across the world, it definitely would. But this is the formula we're going to use just because it's a little simpler than trying to take into account other factors. So this formula gives you the height of an object after a certain amount of time has gone by. And it's negative 16t squared plus v sub 0 t plus s sub 0. Now, this negative 16 is from gravity. If you're in physics, you might see negative 9.8. That's meters per second. If you're dealing meters per second squared is the acceleration due to gravity. This is the acceleration in feet per second. So, a little different. So you have to use units of feet and second if you're using the number 16 right here.
So if you were doing something in meters, you could just swap that out for a 9.2.
Yeah, I believe it's 9.8 meters per second is the equivalent of 16 feet per second.
Are we going to be doing that here?
No, we usually just stick with the feet per second. V sub 0 is an initial velocity that something is thrown at. So like if you were to throw a baseball, it's the speed it leaves, just like the millisecond it leaves your hand, how fast is it going? And S sub 0 is an initial height. So if I was throwing a baseball, it might be like 4 feet off, when I release it, it might be like 3 or 4 feet off the ground, whatever. Or if you threw something from the top of a building, the initial height might be the height of the building plus the height you are that you released it. Okay. If it says ground level, then there is no initial height. So it says a model rocket is shot straight up from the ground with an initial speed of 64 feet per second. At what time will the rocket be 50 feet above the ground? Now, if you think about that, think about what's going to happen when you shoot the rocket. How many times will it be 50 feet above the ground? Twice. On the way up, on the way down. So it'll hit it twice. And both answers should be positive because we're finding a time. Negative time would be before we even launched it. Okay? So it says a model rocket is shot with an initial velocity of 64 feet per second. So that we're going to fill that in. So negative 16t squared plus 64 feet per second plus the initial height, but it says ground level. So what's the initial height?
0.
0, so you don't need plus 0. And the question is, when will it be 50 feet above the ground? So S sub t, that's the height that you're solving for. So there's my equation. Okay, now I know we could use quadratic formula. We could get everything on one side again like we did. I'm going to show you guys a different way to do this one. We can do it on the calculator instead of trying to use quadratic formula. Okay. And the way we're going to do it is we're going to do two graphs. We're going to put 50 in y1, and we're going to put negative 16x squared. You can't use t, you always have to use x on the calculator. So negative 16x squared plus 64x in y2. Now, x is my time. What values of time make sense in this problem?
Seconds.
So that's the unit, but what kind of numbers would you always have to get for time? Positive. So it doesn't make sense to look at negatives on my x min. X max, well, I don't know. That's how long it's in the air for, right? So I'm not sure how much to look for that. What's the lowest height that this rocket is ever at? 0, because it's from ground level. And the highest we don't know. Let's guess 100 feet. If you know the physics, you could figure out, if you launch it based on gravity, how high it's going to go. But we don't have to worry about that. The calculator is going to pretty much tell us that. So there's a line at 50. That represents 50 feet. There's your rocket. So I set my x max way higher than I needed. not way higher, but I probably could have set it to 5. So it says, when will the rocket be 50 feet above the ground? Everybody said it happens twice. Well, where does it happen in this picture? Where they intersect. Second, calc, intersect. I'm going to do the one on the right. If someone can do the one on the left, that would be helpful. And the way you do each one separate, pick a point on the blue, doesn't matter where. Pick a point anywhere on the red, even if it's off the screen, it doesn't matter. I can move it on the screen if you want to see it. And now the guess is how you decide which one you want. I'm going to put my guess closer to the one on the right. If you want the one on the left, just move your guess over there. So on the way down, at about 2.94 seconds, the rocket is at 50 feet. And does anybody have the time on the way up? Yeah.
1.06 seconds.
1.06. Thank you. Any questions on that?
You can just write and the and sign was no.
Yeah, that's fine. Yep, 2.94 and 1.06 seconds. Now it says two questions here. What is the maximum height? And when does it reach it? Well, for a lot of parabolic motion problems, especially from ground level, the maximum height occurs halfway through. Okay? So if you know it hit the ground at 4 seconds, 2 seconds was the maximum height. Now, if you launch it off a building, that changes it a little bit. But for our problem, it'll be halfway through. But we don't really have to even know that. All you have to do is second, calc, and pick maximum. Okay, I don't know if we've done this one before. The way it works is, okay, I'm on the wrong curve. I did second calc maximum, and I'm on the blue. I don't want the maximum of the horizontal line. There really is no maximum. If I hit up, now I'm on the red. Okay, so that can happen. But pick a point somewhere that you know is definitely to the left of the maximum. It's going to put a dotted line in, saying, all right, I'm going to look between here and, let's go over here. Definitely to the right. So it's going to look between the dotted lines for a maximum. Now the guess, it doesn't matter because there's only one maximum between those two. So you can put the guess anywhere you want. Now it says the maximum is 2.000002. But really, it's 2. Okay? So the maximum occurs at 2 seconds. And what is the maximum? Yep.
Well, I got a different one, so that like plugs it in.
Double check your equation looks just like that.
Yeah, I think so.
I got 1.999.
Yeah, so
Yeah, the 1.999, that's fine. Yeah. If you go 1.9999999, it's basically 2. Right? So the maximum occurs at 2 seconds. And I just cleared it, but what was the maximum height?
64.
64. Okay. So max height equals 64 feet. Yeah, 64 feet. Max occurs, max height occurs at 2 seconds.
So why was ours different then?
I don't know. It's hard to explain because my calculator, it's the same one. Did anybody get the one I got, 2.00? And so you got that, and a lot of you got the 1.999. It could have to do with exactly where you put your guess. Could have had to do with where you put the min and max, those first 2 choices. Also, it looks like you're using the color ones, he's using one that's not, so it could be just a little bit different in the operating system, how the calculator finds a maximum. So it's probably a computer thing, real fancy computer thing. That's why it was a little different. Probably comes down to programming. Yeah. All right. Any questions on that? Okay. Alright. So last thing we'll look at here is what's called a piecewise defined function. It's just a fancy way of saying like you're going to do two graphs on the screen at the same time. That's all. So in a piecewise defined function, it's where the domain is split into several parts and you graph each part. So an example might be like, okay, if you give me a value less than 30 for x, I'm going to use this formula. If you give me a value bigger than 30 for x, I'm going to use a different formula. So the formula that you use to evaluate depends on the value you're given. So like in this one, it says if you give me a value less than 1, I'm going to use the top formula to tell you the answer for y. If you give me a value greater than or equal to 1, I'm going to use the bottom formula to tell you the answer for y. And I mean, you could split it up more than that. You could say, well, if you're less than 1, I'm going to use this. If I'm between 1 and 4, I'll use this formula. And if I'm bigger than 4, I'll use this formula. It's just a different formula depending on what number you're given. The big thing, I want to show you how to graph this. So graphing this is pretty similar to graphing anything else. The only difference is you have to use parentheses, okay, around your graph and around the condition for when to graph it. So this top one is a parabola. If all I do is type in this, and I actually type it correctly, 3 minus x squared, the calculator is just going to draw a parabola. That's not a good window, but it's just going to draw a parabola forever. It's going to draw the whole thing. I only want it to draw that parabola when I'm less than 1. So this is how I tell it to stop, basically, and not keep drawing after 1. Put it in parentheses. And then next to it in parentheses, the parentheses are important, put the condition. Only draw it when x. And now we've never used the less than sign, so I'm going to show you where that is. It's under second, test, second, math. That's how you get the less than sign. And I'm going to do it again for the bottom one too.
I can say that again.
Yep, I'm going to do the bottom one right now. Okay, so now for the bottom one, you're going to type it in, but you want it in parentheses. So start with x cubed minus 4x. But I don't want it to draw this cubic everywhere. I only want to draw that part when it's bigger than 1. When the x value bigger than or equal to 1. So next to your graph, put a parenthesis, put in an x, and then second math. That's how you get to the inequality. And this time you want greater than or equal, which is number 4 on mine. So now when we graph that, we're going to get two different graphs. One graph we're going to get when it's less than 1. The other one when it's greater than or equal to 1. Yeah.
You're saying there's like a math button?
Yep, second math, the third button down on the left. That's how you get an inequality. Well, it's the quickest way, I think. Okay, let's hit graph. Watch the parabola this time. It's going to draw it, draw it, draw it, draw it, stop. It just stops. Now it draws that horizontal line. I can't really get rid of that. So if you wanted to see what this should actually look like, it should look like this. That horizontal line, I can't get rid of. It should just be all black. So it's part of a parabola, and then the other part is a cubic. Now, One thing the calculator doesn't do is it doesn't show me where I should have an open or closed circle. On the first one, which is in blue, on the end of that graph, should it be an open or a closed circle? Open, yes. So technically, that should be open. That's really exaggerated. And how about on the one in red? Closed, because it's equal to. So the domain there is all real numbers. You can plug in any number from negative infinity to infinity, and I can tell you where to put it. It's either going to be plugged in here or plugged in here. Okay? So even though it's not connected, that's called a discontinuous graph, the domain is still all real numbers. It goes left and right forever. And it also goes up and down forever too, but I'm not really worried about that. So any questions on how to graph a piecewise function? That's how you type it in. Just using parentheses.
Can I look at that?
Yeah. Just,
Whenever I try to graph it, it just says there's an error, but it looks
an error, and you use the minus sign, not the negative sign, for all your double check. That could be it. Sometimes people mix up the minus and the negative. Was that it? Okay. Okay. Any questions on that? So that's a piecewise. So piecewise functions, they just look a little different. Sometimes they connect, sometimes they don't.
So if you ask us to do that, what do you want for a, do you want us to just graph it all this on a piece of paper on a test?
If it's on a test, I might say, if you graph the following with a standard window, and I could give you 4 choices, and say which one of the 4 choices would this match up to, and this would be one of the 4. If I had you sketch it by hand, I'd just have a graph printed on the test already, and I would just say sketch the following piecewise function, but you'd also be able to use your calculator to help.
Yeah, so you can do it kind of roughly with the points.
Yep. Yep. Any other questions on that? All right, so last thing we'll look at really quick. If you already know most of this, you don't have to write down what you know. But I'm just going to go over y equals mx plus b and how to find slope. Sometimes I skip it, but just in case anyone doesn't remember, I'll go through it really quick. So, I already said this, but what's the slope-intercept form of a line?
Y equals mx+b.
Yep. And what's the m? Slope. B?
Y-intercept.
Y-intercept. Okay. So, if you were to draw that, that's the shape of a line. Slope-intercept form. Okay? It doesn't curve, it doesn't turn. Like we've been looking at a lot of graphs that are much fancier than this, but slope-intercept form is called a linear function. It's a straight line. Any questions on that? Again, I'll put the video online, so if you really want to write something down, you can, but it's a lot of review stuff here. The slope and the y-intercept have to be this kind of number. What is that symbol for again? Real. Yeah, we're not dealing with imaginary slopes and intercepts. And in order to be a linear function, you can't have a slope of 0 right there. If you did, you would have this. Y equals and a number. That's called a constant function, which is a line, but it's not a linear function, it's a constant. Okay, so in order to be linear, you have to have a non-zero slope. All right, this actually is going to tie in with this. So in example 1, I'm going to practice finding the slope. Does anyone remember what's the formula for slope?
Rise over run.
Yep. Rise, I heard some people say rise over run, that's correct. You can also say change in y over change in x. So what I've basically done is I've given you some information on the left, and I want to see if I can find an equation using the numbers on the left. So it says a house was purchased 10 years ago for $60,000, and now the house is worth $85,000. And then the second part is using that equation to do something. So, what was the original price of the house? $60,000. And you could consider that at like year what, when it was $60,000? Year 0, okay, in the beginning. So, we have 0, 60,000. And that looks confusing. I'll just do it like that. So 0, 60,000. And now 10 years later, the house was worth 85,000. So how would you write that as a coordinate?
85,000.
Yeah, 10, 85,000. And now we could find our slope. So the slope is y2 minus y1 over x2 minus x1. There's your slope. What's 85,000 minus 60,000? 25,000 and then divide by 10.
2,500.
2,500. So that's your slope. So each year the value of the house is changing by $2,500. That's the change in the value of the house. So that's your slope. What's your y-intercept? 60,000. It's the y value when x is 0. So now if you wanted to find when the value of the house was $71,250, where would you plug that in? You'd plug that in for y and solve it, either with algebra or you could use the graphing calculator. Okay, so really quick, that's how you find slope. Two special cases with slope. A horizontal line, perfectly flat, has a 0 slope. Vertical line is undefined. Okay, so those are two special cases. When you have a horizontal line, just to kind of show you how it looks, it's always y equals a number. Y equals 2. Y equals 3. Vertical is x equals a number. So what would be the equation of the horizontal line that goes through the point 2, 3? That's same hint I just gave you. What is it? Yeah, y equals 3 will go through every single point that has a y value of 3, including the point 2, 3. How about the vertical line through the point 2, 3? Yeah, x equals 2 is a vertical line, which you can't draw on the calculator, that goes through every single coordinate with an x value of 2, including 2, 3. So those are kind of special cases. Okay, how would you change this to slope-intercept form? Like in general, you have to do what? Get y by itself, solve for y. And the advantage to getting y by itself, I think it's easier to graph if you're using rise over run. You can't really tell the rise and the run here. But you'd have to solve for y. Any questions on how to get y alone? That'll definitely be on a test. Point slope. It's another way to write the equation of a line. We don't use it as much. It's handy if they give you a point and a slope and you don't want to worry about the y-intercept. So if I asked you to write the equation of this line, the slope is a half, and it passes through the point -2, 3. What's my, well, let's start with -2. What is that?
X1.
That's your x1. And what about 3? y1 and 1/2? So, and if you fill them in, you get y minus y1 equals m times x minus 2. Now, is that y equals mx plus b? No, y is not by itself, but if I wanted, I could distribute the half and then add 3 and get y equals 1/2 x plus 4, if you wanted to rewrite it. If they don't ask you to, I wouldn't worry about doing it. Okay. This form we don't use very much. We use that a lot when you solve quadratics. Get it equal to 0. With lines, we don't really use it. So I don't really worry a ton about general form. Parallel. Lines are parallel if what? Same slope. Different y-intercept. Same slope, same intercept. That's the same line. Okay. So 2 lines are parallel if they have the same slope, different y-intercept. I was going to ask you that, but I just showed you. 2 lines are perpendicular if their slopes are opposite reciprocals. For example, what's the opposite reciprocal of 3/4?
-4/3.
Yep. Very good. Okay, so you guys know all that. So what I might ask you to do is, and we can go over one from the homework, I'll give you a line and say, tell me one that's parallel to this one and passes through that point. Okay, again, back to algebra 1 kind of stuff, but we'll go over it in the homework. I think, is this the last thing? Yeah. So the last thing is a linear inequality. What's the only extra step if you have to graph something like that?
You have to shade it.
You have to shade it, right? And the way I remember which way to shade is if it's less than or equal to, you shade below. Greater than or equal to, you shade above. Now, one other thing about the line you draw, it can be, yeah, if it's solid, it uses the equal to. It's dashed or dotted if it doesn't have the equal to. Okay, but that's it. Other than graphing the line, you just shade for these, shade below. For these, shade above. So if I was going to graph that one, the first thing I would probably do is this. That would be what? Negative 2/3 x. I would get y by itself. Graph that. Would that be solid or dotted? Dotted. And where would I shade? I'd shade below. Kind of messy with the 4/3 intercept, but you could do it if you had to. So that's a really quick review of slope y-intercept. It's not really pre-calculus, but it's important to kind of know it. Okay, so homework tonight is, first part is from the, starting with the integer step functions and that stuff. So it's page 31. And then the second part is all slope y-intercept. So we might need to spend a little more time on this if we don't remember as much about that. We'll spend some time on that tomorrow. Okay, but the video will be online after your class today.